Hello, my name is Ghamini Sumanasekera. I'm a professor here at University of Louisville in Kentucky. The first lecture of the lecture series intended for Perm State students. So today I am going to talk about some diffraction phenomena. So mostly for diffraction from crystalline solids. So let me get started. So the presentation here. Okay, so this is about diffraction in crystals. So this is the first in the series. So I'll be giving you 10 lectures on various topics. So when you talk about crystal diffraction, so actually the whole activity started when Laue, Max von Laue discovered this diffraction phenomena using X-rays. So in 1912, so for that he won the Nobel Prize in 19. So you can see here, so he used this X-ray tube with actually broadband X-ray tube with polychromatic X-ray light. So when incident on the crystal, so it formed some very regular pattern of these spots we call the diffraction pattern on a photographic film. So this started the work of diffraction, basically to study atomic configurations and crystalline structure of solids. So if you look at some crystals with crystalline planes, so here I am showing you parallel planes like 100, 200. So typically these lattice planes have space in about 1 angstrom. So to probe any atomic features, you need to have wavelengths in the order of that angstroms, right? So X-rays have that wavelength. So that's why we can easily probe atomic or crystalline atomic structures using X-rays. So today, actually, people use electrons and neutrons to probe materials in addition to X-rays. So we all know X-rays, electrons, and neutrons, they all have this quantum wave particle duality, right? So you can consider them as both particles and waves. So X-rays, basically, they are electromagnetic waves. So that means you can write your energy as Planck constant time the frequency, or as given by velocity of light divided by lambda. So if you calculate from here, lambda is given by hc over E. So if you use lambda about 1 angstrom, we are talking about energies. You can use H and C values. If you calculate, your energies are about tens of kilo electron volts. That's the important thing to remember. But if you consider electrons, they are particles, but if you use wave particle duality, we can define the de Broglie wavelength. So that de Broglie wavelength is given by this momentum equals h over lambda. So now again, if you use lambda about 1 angstrom, but here we have to consider the electron mass also. So then we know how to write momentum in terms of energy, kinetic energy as square root of 2me. Now, if I use lambda about 1 angstrom, now we are talking about energies of 150 electron volts. These are much smaller than X-ray energies. They are in kilo electron volts. So now if you consider neutrons, again, neutrons are particles. So we can define our de Broglie wavelength given by h over p. Again, p is square root of 2me. So now we know the mass of the neutron. So if we use lambda, that's our atomic lattice space in atomic distance, about 1 angstrom. So you find energy to be very small, right, compared to the previous two. Now we are talking about only 1/100th of electron volts. So you can see how the energy ranges for X-rays to neutron. So because of that energy difference, we should be able to probe differently. So if you typically take here in the left side, I am showing some X-ray diffraction pattern taken from this yttrium aluminum oxide. So this shows very regular pattern, right? So this, looking at this diffraction pattern, actually somebody can easily see there's a good symmetry, right? So they have nice symmetrical pattern. So that symmetry pattern of the diffraction image is a reflection of the symmetry of your crystal. So by looking at that, sometimes you see maybe rectangular square fringes. Sometimes we see hexagonal kind of structures. So depending on that structure, you can tell what the symmetry of your crystal. So if you look at these three radiations we talked about, so they have some complementary uses. So if you consider diffraction, so here photons we are talking about, right? So going from 10 to 100 of kilo electron volts, since it has very large energy, we have very large penetration depth, right? They can penetrate deep into the solid. So that means you can easily probe three-dimensional features of a crystal. So also, so this later we are going to talk about X-ray being scattered by these electrons in the solid. So this mostly this diffraction pattern results from the scattering of these X-ray waves from the electrons. So if you have more electrons, so that means something that has high atomic numbers, so they will give you better results because you get more scattering. So if you look at the diffraction from electrons, so electrons are charged particles, right? So that means they have strong interaction with the matter because charged particles always interact with charged particles, right? So your atoms, they have electrons and even protons. So because also we know the energies are smaller, that means penetration depths are smaller than the X-rays. For that reason, these are mostly suitable to study the surfaces, not the bulk of the materials. So lastly, neutron diffraction. So the neutrons, they are neutral particles, right? So that means they have better efficiency for light elements. So also, so they can probe inelastic scattering. So mostly the first two diffraction, they are mostly coming from the elastic scattering, but neutrons, you can study features coming from inelastic scattering, things like phonons, the lattice vibrations, right? Also, since they are neutral particles, they can even interact with the nucleus of the atom, right? So that means the magnetic moment of the neutron can also interact with the nucleus. Also, that magnetic moment can interact with the magnetic moment of the electron. So that's why I think neutron diffraction is more useful when you want to study scattering from magnetic entities. So they can be easily used to study something called the magnons, like phonons. So here we have, due to the magnetic moments, you have waves called magnons. So these are some features we can study from these three different diffraction methods. But in this lecture, I'm only going to concentrate on X-ray diffraction and electron diffraction. So typical, if you consider electron diffraction, they have several experimental methods. So basically people like to study the single crystals. That means the entire crystal has one specific crystalline structure. Then also sometimes we have polycrystalline sample, right? Certain part of the crystal is one crystalline structure and other part is different crystal structure. So we call the polycrystalline structure. So if the kind of radiation you use for study these structures, so for single crystals, so you can use either monochromatic light, that means you have only one wavelength of your X-ray. So that's monochromatic. So we call that a single crystal method. Or you can use polychromatic light. So you means you have white light kind of, your radiation has many wavelengths. So that can be used to study single crystals. So that's called the Law method. So then if you have polycrystal material, you can only use the monochromatic light because already they have polycrystalline nature. So you can only use monochromatic lasers to, monochromatic X-rays to study the properties. So we call this a Debye method. So there's no point of use in polychromatic because already you have polycrystalline material, right? So these are standard methods we use for X-ray diffraction. So in the Law method, like I said, you have sample, mostly single crystal material, but you use polychromatic X-ray beam. So then you will see this nice diffraction pattern on a photographic film. But if you use the Debye method, so here we are talking about polycrystalline sample, right? So polycrystalline sample, but we use monochromatic light. So then you will see this nice diffraction cones. So coming at this 2θ angle, we'll talk about that one later. So you will see this rings of these spots or that crystalline, the diffraction pattern. So from the polycrystalline sample with this Debye method, mostly you are seeing the circles of these dots or the fringe pattern. So we'll talk about this one later. So this last figure shows you standard X-ray setups. Basically, you have this is for the Debye method. You have this sample here. So you have this monochromatic light coming here. So that's the source. So they detect around this goniometer. So we call this a 2θ technique. So depending on that one, you can get the information. So basically, you have fixed your source, then you move your detector around this goniometer circle. So next, I want to talk a little bit about how you generate X-rays. So that's everybody knows. If you have electron beam, high energetic electron beam, if you can bombard on some specific metal, so that will emit X-rays, right? So what you need is basically some filament to heat your this electron, we call the cathode. So basically we use things like tungsten as the electron emitter. By heating, by thermionic emission, you can emit electrons, so that when the electron is bombarded with some metal here, so if you want particular wavelength, so you can use like copper. Then you can use molybdenum, iron, or any of these metals. So depending on the metal, you will get some X-rays with specific wavelength. So if you look at electromagnetic waves here, typically we are going from high wavelength. So we are talking about like radio waves and things like that. So then we are getting smaller wavelengths coming through here, get into like angstrom level. So you are getting X-rays, right? So before that, you have ultraviolet and visible light here. So once you get to wavelength about angstrom range, you are getting this here. So that's the typical electromagnetic spectrum. So if you look at X-ray, so like I said, you have this electron bombarding on the your target material. So what happens is, because these electrons are getting slowed down or absorbed, so you will see this kind of absorption intensity. So you can see your intensity is basically for different energies. So going from low energy to high energy, this is basically we call the background spectrum, right? So this is mostly coming because high energetic electrons are getting slowed down or getting absorbed. But at particular energy, you will see these sharp peaks coming. So that's because these electrons are going to eject some core electrons of that target material, so leaving some vacancies in that core electron shell. So then the higher energy electrons will try to occupy that vacant spot. So in the process, it will emit radiation. That's where you get this sharp peaks here. These are the X-rays we are talking about. Typically here I show you like K alpha and K beta. So this is typically, if you look at your shells, everybody know the principal quantum numbers goes from 1 to whatever the number we call is K, L, M kind of shell structures. So now each, say if you take a K shell that n equals 1, you have something called s orbitals, right? So if you have a L, so that is n equals 2, you have p and s. So if you have n equals 3, that's the m orbital, you have spd, so on. So this K alpha we are talking about is something from L orbital to s orbital transition, because with the electrons we emit electrons from this L shell. So then the higher energy electrons will fall from here to here. So then you get emission of X-rays we call as a K alpha radiation. So if you have some electron falling from M shell to S shell, so then we have K beta radiation. So this is what I want to say. Continuous spectra we are here. Also we call the white radiation. That is because of the by the absorption or stopping of electrons by the target. That's what this continuous curve. So then characteristic X-ray peaks, they are coming from due to the ionization of the inner shell. So you ionize this core shell. So then the outer shells, the electrons will try to occupy that vacant shell. In the process, they emit electrons. K alpha coming from L to K. So K beta comes from M to K. That's what we talked about. So then the powder diffractometers, there are different. Here I show you how things are happening. So you have electron the tube here. So then the electron, the X-ray radiation is coming here and falling on the sample at the center of this goniometer circle here. So then you can measure the diffracted light. So this is 2 theta curve. So then also you have ability to rotate the sample in around this in the phi direction. So if you look at, so this is how the X-rays are going to be on the specimen. This is your sample here, right? So you can get how they are going to from tube to detector. So this is standard how all these collimators, slits, and other the typical instrument is set up here. So now I think what we are going to do is look at something called this Bragg diffraction law. This is about X-ray getting diffracted from series of atoms in a crystal. So this is applicable for any photons like X-rays or electrons or neutrons. So this is more general situation. Here you can see this is my atomic plane. So you can see atoms here. So this is the distance between the two atomic planes. Now we have like two X-ray waves, right? So this X-ray or electron or neutron, we can consider they all as waves, right? So this first one, the red one, is getting reflected like this one. So then the second one, the green color wave, that's getting reflected from this one. If you now look at what is coming here, so if you look at this blue and green waves, so starting from here to here, we can see this green one is traversing length, right? So because you can see this distance are the same, this distance and this distance are the same, but green one is going through this additional 2 distance. So that is given by, if this is d, if this angle is theta, this is d sine theta, then this is also d sine theta. You have this additional path difference we call 2d sine theta, right? So what this diffraction law says is, if this total path difference 2d sine theta is integer number of your lambda, so you have diffraction condition. So that means more like having constructive interference. So if they are like odd number of lambdas, so that becomes more like destructive interference. So the condition is, Bragg law says, condition for specular reflection, your 2d sine theta, that's the path difference, should be n times lambda. You cannot have like a fraction of like a half lambda or 3/2 lambda, things like that. You have to have this n as an integer. That's the condition for diffraction. 2d sine theta equals n lambda. So this d means the distance between two atomic planes. So typically we write that one as HKL. HKL are the Miller indices of a given atomic plane. So I hope everybody familiar with the Miller indices. So n is, remember, that's a integer. If you take one simple example, so if you have diffraction pattern coming from X-rays from aluminum, so with the lambda, so it's about 0.7 angstrom. So second order diffraction, so that means your n is 2 here, right? So with the cubic cell, so everybody familiar with the cubic lattice, so we'll talk about that one later. So that you see that diffraction pattern happening at 2 theta equals 20.2 degrees. So if you want to calculate A, how do you calculate? So from the diffraction equation, we know 2d sine theta equals n lambda, but here n is 2 times lambda. So then from here you can find d as lambda over sine theta. So remember, this is 2 theta, then theta is 10.1. If you calculate that one, you get 4.04. So we then actually we can show that d is almost like the lattice parameter A for the this FCC lattice here. Then little bit more about the Bragg's law. So this is very important thing to understand. So if you have this X-ray light like 1 and 2 getting reflected, so you have 1' and 2', they are the ones going to get interfered, right? So now if this is, we are talking about the diffraction from these two planes, 1, 0, 0 plane. So then if I have plane diffraction happening from 2, 0, 0 plane. Everybody remember 2, 0, 0 means in the Miller indices you have 1/2, right? So basically, so this is, we are talking about this distance is 2, 0, 0 is actually 1/2 of the 1, 0, 0 distance. So now if you look at your diffraction. So when we have a path length difference, this n lambda we talked about, right? That should be 2d sine theta. So that actually with that we are changing that d. So that's why you need to be careful. If I consider the first order diffraction, say n equals 1, if I have 2d, this first situation 2d 100 sine, so this angle coming from 100, but if I study the diffraction coming from 200 plane, like here this diffraction from 1 prime and 3 prime, so that's the coming from the 200. So in that case, your angle will be different because your d is going to be different now, right? Because it's almost half of that. You need to understand when that happens. Here, this is happening from 1 prime and 2 prime. Here it's happening from 1 prime and 3 prime for 200. Now let's look at some general theory of diffraction. So one thing you need to understand is that's what we are going to introduce. So there are two things we have to be familiar with, something called the structure factor, then also atomic form factor. Then also there's something called the geometrical factor. So, but this one, these two things actually determine the diffraction position or the angle as well as the intensity of particular reflection. So that's why I think we need to know the structure factor in order to understand the intensity pattern of the, so because some peaks or the dots are more intense compared to the other patterns. So typically what we are trying to do is, if you have X-ray source here, you can see initially you have this spherical wave. So but at far distance we can assume that to be more like a planar waves. So then when they collide, I think impinge on the crystal, so you will have from atomic positions on the crystal, they are going to send this scattered spherical waves from each position, right? So then you need to integrate over all the crystal here. So then you have detector here at the B position. That's where you are going to look at how the intensity at that point B. So because we need to see how light is scattered from each and every point of the crystal. So this is what I was trying to say. Crystal particular lattice. So everybody should remember, like when you talk about crystal, crystal means you have the geometrical entity called lattice, right? Lattice is just the geometrical points. So each point, then we are going to attach something called the basis or the motif. Sometimes your motif can be only one atom, or sometimes that motif can be two or even hundreds of atoms, right? If you take a polymer crystal, so or protein crystal, so this motif will have many atoms, right? But they all have one specific lattice structure. So that means crystal, when you talk about crystal, there are two things, lattice and the basis. Sometimes we call this a motif. So in crystals, for a particular lattice, the intensity can be modified. Sometimes they can be even missing reflections. So that's why we need to understand the position of the diffraction spot. So that what is that angle where you get the diffraction maxima or minima or missing pattern. So that's determined by the lattice. So that's the geometrical lattice space. So then the intensity, whether it's a stronger peak or weaker peak, that is going to be determined by the basis. So what is in that lattice? So what you are going to attach. So that's what we need to understand. So that means when you talk about diffraction pattern, the two things we are talking about, right? So position of the diffraction spot, So later we'll talk about the reciprocal lattice. So other one is the intensity. That's the motive determines that intensity. So now let's look at the diffraction theory a little bit. So if I have, this is my crystal or the material. So this is the incoming wave. If I assume this to be a plane wave, so starting from spherical, but we can, I think, approximate it to be a planar wave. I can write that plane wave as EI k dot r, right? Everybody knows how to write a plane wave equation. So this I can write this plane wave EI k dot r. If you want, you can write minus omega t, right, in time dependence. But in spatial dependent, I can write this one as EI k dot r. So then if it get scattered or diffracted, then outgoing one, this one has your wave vector k, right? The diffracted one have different wave vector k prime. Then you can draw, write the wave as EI k prime dot r, right? So that's how you have. So then if you look at what is the path difference between these two, that basically that is this one plus this one, right? But this distance, we know that's basically you just you know that unit vector in this direction is k over k magnitude of k. Then you multiply by this dot product of r, so that will give you this distance. So what is this distance? We know the unit vector in that direction, k prime over k magnitude. So if you multiply by r, you dot product of r, you get this distance. Then your path difference is basically this one plus this one. But you can write this one in more easy terms. If I have first one come in like k, so then going out with k prime, then your difference will be in your the wave vector difference is k prime minus k, right? So then we also know k and k prime, the magnitude is not going to be changed because these are elastic scattering we are going to talk about. So the magnitude of k and k prime are the same. So now if I take k minus k, so difference is k. So this is k prime. So the difference will be, this is your k prime minus k, right? So that is basically, if this is theta, this delta k is given by, because this distance is the same k, 2k sine theta, right? K sine theta plus k sine theta. We need these things in the future. Okay, now when you talk about this scattering, first we need to start from single electron, right? If I have one electron, you have X-ray come in here. So we know the X-ray is electromagnetic wave. You have electric and the magnetic field perpendicular to that one. So then this one, this electron beam will be diffracted this way, right? So it's some angle. So we can easily calculate this scenario. So, but if you have two electrons, suppose I have one electron here and two electrons here, then again X-rays come in this K and getting diffracted like we discussed before, right? K prime. So now if you have an atom has many electrons, right? Z number of electrons. So then how do we calculate that? So that's not simple, right? So if you consider atom, so we know nucleus, so then we have electrons in these different orbitals, but these electrons also have this we call the electron cloud, right? There's some distribution of electronic charge. So then, because we need to now consider, here we only consider one electron, two electrons, now we have to consider all these electrons, right? So that's why we need to consider the charge distribution of this atom. So that's where we are going to talk about the atomic form factor and things like that. So then that is one atom, right? But when you're going to talk about crystals, then we need to expand that one to the one-dimensional atomic plane. So here one atoms, two atoms, three atoms. Then now we are talking about diffraction coming from one line of atoms. So this is one row of atoms, right? Then we need to consider two-dimensional. So we have atoms in two dimensions. So in this case, you need to consider diffraction happening actually in all the directions, right? This is like three-dimensional cones here. So then that is two-dimensional. Then we need to talk about coming from three-dimensional crystals. So that's not easy, right? So it's pretty difficult task to consider diffraction happening from all these electrons in this entire three-dimensional crystal, then from each atom and from each electron. So then we need to have some way to simplify that. So what we do is, we all know in crystals we can consider a unit cell, right? So each unit cell has certain lattice, but also it has this basis, right? So you have, so in this one I have this simple unit cell here. In the unit cell I have three atoms, so we call the basis. So we have R1, R2, R3. Now only you have to consider diffraction happening from this unit cell. Then we can expand or extend this unit cell for the entire crystal, because the crystal has translational symmetry. So because of that, we can consider just the unit cell and expand it to the entire crystal. That's the whole idea. So now let's go ahead and start this analysis. So like I said before, I have this X-ray. So this come in as a spherical waves. So then this becomes, we can assume it to be planar waves. So suppose this has a wave vector k0, then I can write that wave coming to this point P. So what is the point P? So then this vector here, this is, we call this is R vector. This is simple R, because later we are going to integrate over this R for the entire crystal, right? So that's the important parameter, this R here. So now for this P, how do I write the incoming wave? Because it's coming from here to P, right? So I can, that means my this vector is going to be R plus R. So then I can write the amplitude of that wave coming to point P as some constant times EI. So the wave vector is K0 dot this R plus R. If you want the time dependence, you just write like this. So that is the incoming wave to this P. So now what important is what is coming out from here to this is where your detector is B. So what is coming to B is from P is we call a B, right? So that is some part of this one, right? AP times. So whatever you have this atomic, this energy, so the charge distribution here. Suppose this charge distribution we write like rho R. So this is the charge per unit volume. So that rho R, so times, so then it is your, I can write the wave vector I, this one. So what is the wave vector now in this direction is K, but this, what is the wave in this direction? So that is R prime minus R, right? So because this is R prime, this is R, so then this will be R prime minus R. So this is the wave coming to B. So now we know AP. AP we can write from here. If I plug in AP from this one, what I get is, yeah, this rho R was the electron density. So then I can write AB as, so this is AP, the incoming wave, then rho R times this one. So now just separate all the constant terms here and take only the R terms here. So because you can see this R I can take to this side, then this becomes K0R. So then I have only KR here, right? You can write this one. Everything else, these are more like constant terms, because we need this rho R terms. Eventually we are going to integrate over R for the entire crystal. So then total scattering from the entire volume I can write as, because this is a constant. So this is proportional to rho R times E minus I, this K minus K0. That's the important part. So we call this one delta K. That's dot R. Then we have to integrate all over volume. That's the final thing. That's all you need to know. So if I rewrite this one, I can write the intensity. Actually, that is the amplitude, right? intensity is proportional to square of that amplitude, then I can write that one as is rho r ei, the square of that one. So this is, I can write rho r. I can write k minus k0 as delta k dot r d cube r square. So if you look at this one, what do you see here? This is nothing but the Fourier transform of your rho r, right? So if people are familiar with the Fourier transformation, this is basically the Fourier transformation of your rho r. So this delta k means k minus k0, right? Actually, this is 2k sine theta, if you remember. So the diffraction intensity is basically the square of the Fourier transform of the your electron density. Everybody knows how to calculate the Fourier transformation of any. This is going from real space to your momentum space, so like that. Okay, so now also another important thing is this rho r, that is the charge density, right? So many properties in a crystal, that's a very important thing. Crystals, we have the spatial or translational symmetry. So even the electronic is, I think we have translational symmetry. So that means I should be able to write rho r as a sum of this term, because we have this G is the reciprocal lattice translational vector. Like we have translational vector in real space, right? So you can go from one lattice point to another lattice point by translating from that translational vector. So that is determined by this primitive vectors. Same way in the reciprocal lattice, we have this reciprocal lattice points. So you have the vector G, so that you can go from each reciprocal lattice point to another lattice point by translating with vector G. So because it's all because of this translational invariance of rho r. So this is the translational vector in real space. You can write r mno as a1, a2, a3 are the real space primitive vectors. So mno are all integers. So then this is what the translational invariance means. If you go to any rn point by this vector, you have the same charge density. That's the translational invariance. So that we know this G dot R M1. So this is the unit reciprocal lattice vector. So this is the real space lattice vector. So if you take the dot product of this one, this is always 2 pi times integer. Right? So that's something everybody should be familiar with. So now this is where we started, right? This your intensity, that's a function of your delta k. Delta k is k minus k0. That's the square of your Fourier transform of your rho r. So this rho r, because of translational invariance, we write rho r as a sum of these g vectors. Remember, these are the reciprocal lattice vector unit, the translational vector g. So now if I plug in that one here, so delta k I can write as rho r, I can write this one, I can write as this one. So then I have E minus I, so then this G comes here with this one, then you get dqr. You can easily, so basically you substitute this one into this equation. So now if you take this one, what is this one? So this is nothing but delta function, right? So this is the delta function definition. So if you plug in that, use the property of the delta function, if you do the integral, we know, then you can substitute G as delta k, right? So then I, if you do this one, your I becomes simply rho G times. So then this d cube r is basically volume. So you get the volume square. You can easily do this integral. So what happens here? You get this the total intensity when your delta K is same as your G. So delta K is K minus K0. That's the difference in your incoming and outgoing wave vectors. G is the reciprocal lattice vector. That is, we'll talk about that one later. So that is, you can see, this rho G is the Fourier transformation of your electron charge density. So that's what we showed now. This is the important thing. Delta K, when delta K equal G, you get this condition. So actually this delta K equal G is nothing but the Bragg condition. Remember 2D sine theta equals n lambda. So we can show that one very easily. Yeah, delta K is nothing but the Bragg's law. So this is, like I said, G dot Rn. So this is the Rn means this is the real space lattice vector. So you can translate any lattice point to another lattice point by this one, right? Because n1, n2, n3 are integers. So G, that's the reciprocal lattice vector that we write as this HKL integers with G1, G2, G3. G1, G2, the 3 are the primitive vectors for in the reciprocal lattice space. So these are A1, A2, A3 are the primitive vectors in the real space. G1, G2, G3 are the if you call lattice vectors in reciprocal space or the Fourier space. So this HKL also integers, but they are also related to the Miller indices. HKL Miller indices are exactly those HKL. So yeah. So now actually you can, somebody can write this G1, G2, the G3 in terms of A1, A2, A3. So like this, sometimes people call this one B1, B2, B3. So just G1. So basically you can write G1 as this cross product of A2, A3. These are the real space divided by this the volume of the real space unit cell, the triple product here. Then G2 is A3 cross A1, G3 is A1 cross A2. So this way you can easily calculate what your G1, G2, G3 if you know A1, A2, A3. So important thing is this G dot A follows this 2 pi times this Kronecker delta. That means G1 A1 is 2 pi, but G1 A2 is 0. So just find that down. Also, this GKL, if you take the magnitude of this GKL, is 2 pi over this is the distance between the HKL. That's another important thing to remember. Yeah, that's what we. So the scattering condition is basically delta K equals that's GKL. So this is somebody can easily show this is nothing but this equation. How can you show that? Like I said before, K0 come in, getting reflected with K. So then your delta K is this one, right? K minus K minus K0. So that is this one. This is nothing but 2D sine theta, right? So then also somebody can easily draw, right? If this is lattice plane, so the distance between two lattice planes is 2 pi over that's D value. So otherwise, this way, K is, you can write like this, delta K. So delta K is, you can write this way. So if you do this one, you get the delta K is, we showed this one, right? It's nothing but 2K sine theta. You don't have to do this one. So delta K is basically 2K sine theta. Equals what is K? K is 2 pi over lambda. Remember, K is defined as 2 pi over lambda. Then you get 4 pi over lambda sine theta. We know then delta K equals the Bragg condition is delta K is G, right? Delta K is G. That's the Bragg condition. Then I showed G is nothing but 2 pi over D. So if you use this one, you get this 2D sine theta equals lambda. It's the same condition. It's pretty straightforward. Now we are going to look at something, a very important thing, the structure factor. So this is the condition we got, right? I, this is the Bragg condition. Then you get your intensity as This is the Fourier transform of your electron density. This is the volume of this one. But we only have to consider this part. That's the only thing. So this controls the actual intensity of the reflection. That's why we need to calculate this rho g KL. So remember, rho r is the Fourier transform, right? So then you can write inverse Fourier transformation like this. So rho r is like this one. That's all you can write as, because this has the charge densities has the translational invariance. So then also, yeah, rho HKL is basically, you can write as the Fourier transformation, right? So this is a Fourier, that's what we showed here. So this is the normalization constant divided by the cell volume. Okay, so one important thing is, so most of the electrons in an atom, so they are centered in a small region around the atom, right? So that means mostly we have to consider scattering coming from the co-electrons, so not the valence electrons. They are more, I think, spread out. So we need to mostly consider the scattering coming from the electrons closer to the nucleus, right? These are more, we're talking about the co-electrons. So that means we can consider the scattering from valence electrons pretty negligible. So now, if you consider, like I said, the unit cell, remember we cannot consider all the atoms in the crystal, right? We only going to consider the atoms in the unit cell. Suppose nth unit cell is located as some position R alpha. So then inside the unit cell, you have the position for each atom in the basis. So now if I write this is my rho HKL, right? So then I can write this one as rho R. So I can, yeah, so this is out. So this rho R I can write as, so it's coming from R prime. So that, but this R prime is R alpha plus that position vector, right? So this R here is, each R I can write as R alpha. R alpha is the position of your unit cell. From with unit cell, you have position of each atom in the basis. So if I plug in R as R alpha plus R prime, remember R alpha is position of your unit cell, then R prime is with respect to that unit cell, what are the R prime positions. So I will show you the, so this is like, this point is my R alpha, right? So with respect to some origin. So from here, I this R primes. So R1, R2, R3. So if I write that way, I can write this one as this whole thing becomes like rho we call F alpha. So that F alpha considers the position of that unit cell. So then you have to add for all the alpha. So that means this with respect to that unit cell. So here we are talking about alpha. Like in this case, I have 3 values of alpha, right? F1 coming from R1 here. So then R2, R3. In this particular one, I have 3 vectors. So then we need to then, yeah, that is coming from all the positions here. So this F alpha is actually, we talk later as the atomic form factor. That tells you how the atoms are arranged in that crystal, so not in the unit cell. So this alphas are all what is inside the unit cell. So this is, we call the structure factor. So that's all we need in the rest of the discussion. So these R alphas are what is inside the unit cell. Okay, so please remember, this is the most important if I want to write like that one. So this is the basic thing you need to remember. Please remember that one. So then also somebody can think the structure factor in simple graphical representation. So because this is the number of atoms in the basis, right? You have to add all the factors. So if you do that one, remember this is 2 pi minus I GHKL. GHKL is, if you remember, that is H times G1 plus K times G2, L times G3. So this R alpha are just your XYZ coordinates, right? So if you get the dot product, you will see that is nothing but this H times UI, K times VI, L times WI. So then you have this EI 2 pi I outside, right? So this is we have yeah, I here. So then you have factor 2 pi in that multiplication. That's why you get these 2 pi terms coming here. So this H, K, L are that G vector that represent the atomic planes. UI, VI, WI are the atomic position inside the unit cell. Now, if you consider this one, this you can think as from each atom in the basis, you need to add all these terms, right? So you can consider this one. This is coming from the first atom in the basis. This is coming from the second atom in the basis, like that. If you have n terms, UF means actually the total, the vectorial sum of that FHKL. So that you can write as this way. So now what is that F alpha inside that term? So that F alpha is nothing but this term, right? Rho alpha, this I dqr. So somebody can easily calculate this one if you use atom as a spherical symmetric object, right? So you can write your d cube r in spherical coordinate as this one, right? R prime sine theta dr prime d theta d pi. So d pi is your azimuthal angle that's going from 0 to 2 pi. Then p theta that's going from 0 to 180. So then r we have to integrate to r. So now the only thing is this g hkl dot r. So we will consider this gkl to be in this direction. So then you can easily write that one as gk r cosine theta, right? If I pick my g to be in c direction, so then if you take this function, that is cosine theta, this one. Now if you separate the variables, you can see there's no p dependence, so that becomes 2 pi. So then only thing you have is this, because these two terms have both r prime and theta dependence, so that means I can write this way. So then if you integrate with respect to, because sine theta dr prime I can write at d cosine theta. So if you differentiate this one, you get e minus I minus e plus I divided by 2. So that is sine gr, right? So divided by gr, you get this expression. So if I put g is basically 2k0 sine theta, right? So if you apply that one, so this is your atomic structure factor. F alpha is given by this one. This rho alpha is basically that charge density. So we have both, only you have to integrate over entire R space, right? So this is very simple integration to do. So we can make it very simple if you take theta as 0. So theta is 0 means it's a forward scattering, right? So then this sine theta over theta becomes 1. So then you get, this is 4 pi rho times r dash squared dr, because this sine theta over theta becomes 1, right? For theta goes to 0. So then what is this one? That is simple, right? Rho r, if you integrate over entire the sphere, that is total number of charges. What is the total number of charges? That's Z, right? Z is the atomic number, or number of electrons in the atom. So here you have some atomic form factor with theta, you can see for theta equals 0 in this situation. So if you consider hydrogen here, you can see this is 1, right? C is 1 for hydrogen. Then if you go to carbon, carbon has C as 6. So you have, this is for carbon. So then you have other elements. So they all corresponding to C. So then for different theta values, you can see how the F alpha changes with respect to theta. So they all decreases for higher angles, right? You have maximum. This is the forward scattering that has the highest form factor. Then it's decreases with theta. Okay, so now I think next one we are going to talk about all the how to calculate the structure factors for different crystal structures. So I'm going to stop here. So then we can start next lesson from where we stopped today. Thank you.